Every new telescope put up in space has always found something they didn't expect, something new.
The James Webb Space Telescope is the biggest, most complex telescope that NASA has ever launched into space.
Telescopes are time machines. Webb will push us back into the realm of the very first stars and galaxies in the universe.
The Webb telescope is designed to see as far back in time as we can possibly see luminous objects, when the universe was maybe 100 million years old.
We have a suite of very powerful instruments to study the atmospheres of planets. Webb will be very helpful to us in the search for life in the future.
Up until Hubble flew, we were using telescopes on the ground, and they couldn't see very far.
T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Hubble Space Telescope, our window on the universe.
When Hubble flew, we knew that it was going to be able to reach out further into the universe, but we didn't really have any idea what was out there. The Hubble Deep Field image was a discovery image of the 90s. What was unique about this was the idea of spending days and days of valuable Hubble time staring at a tiny spot in the sky where there was nothing. When we did a deep image like this, astronomers suddenly saw that there was a richness of galaxies in there, thousands and thousands of galaxies we'd never seen before. Basically a history of the whole universe in one image. The universe is 13,800 million years old. Light travels very rapidly, but the distances are so huge.
Hubble can see in the visible and the ultraviolet with a little schmidge in the infrared. But the things that we want to see now, the first stars that turned on in the universe, the first galaxies, they were probably very bright objects that emitted a lot of ultraviolet light. But that ultraviolet light, with a very short wavelength, as it traverses through a universe that's been expanding for about 13.5 billion years, gets stretched out. So that by the time it reaches us, it's no longer ultraviolet, it's infrared.
After they had the Hubble Deep Field, they said, we can't see far enough. So we need a bigger telescope that's more sensitive and that can look at longer infrared wavelengths so that we can see the more distant universe.
About 13.7 billion years ago, there were no stars in the universe. There was just gas and dark matter. We'd gone through 200 million years of dark ages. Suddenly, the first stars and galaxies would start popping up all over the place. Cosmic sunrise. And so that's what JWST is for, mapping the first billion years of galaxy formation and growth in the universe.
The Webb telescope is the first general-purpose, powerful infrared telescope we've ever had. It opens up what I call the infrared treasure chest. If you were a bumblebee at the distance of the moon away from the telescope, we would be able to pick up the heat that you send out. Infrared is special for astronomers because cooler objects that cannot emit visible light are able to emit infrared.
When we look at the universe, you see there's lots of sort of dusty, dark areas. But one of the great things about the infrared is light can travel through the dust. The dust becomes almost transparent. So if we're trying to see how stars and planets form in their early times, the infrared is the place to be.
If you want to see dim stars, you don't stay in the city, you go out to the country, right? You get away from the lights. We want to see the dimmest galaxies there are to see. Well, the Earth is pretty bright in the infrared, so you want to get away from the Earth, you want to get away from the moon.
Webb needed to be far away from Earth, and it needed to be very cold if it's going to work in the infrared. So if you cool the whole telescope down near the temperature of space, then you can see out with incredible clarity over the first billion years of the universe.
So we're going to a point called the Sun-Earth L2 point. It's 1 million miles away from the Earth on the opposite side of the Sun. And it's a place where the gravity of the Sun and the gravity of the Earth combine to make a relatively stable point that follows the Earth around the Sun every 365 days. So if we go out there and we put up a sun shield, a big umbrella, from that location we can block out the Sun, the Earth, and the Moon at the same time. This is obviously no ordinary umbrella. The 5 individual layers are made of a almost plastic-like material called kapton. 200,000 watts of solar radiation strikes the hot side, and the sun shield will only allow about 0.02 watts to get through. If it were suntan lotion, it would have a solar protection factor of about 10 million. So the telescope and the instruments are exposed to cold space.
The Webb telescope is the most difficult scientific project we've ever undertaken. It's got to unfold itself in space.
James Webb is obviously not going to fit on the top of a rocket, so something that's that big has to be folded. A consequence of this folding up is that we have to be able to do the deployment in orbit. Once we're above the atmosphere, the fairing drops away and James Webb is then sitting alone on top of the rocket, shooting towards the moon and out to its final orbit. The solar panels have to come out very quickly to power it. Over the next 29 days, there's a whole sequence of activities that happen. The very large sun shield has to be pulled out and be separated, and that is an amazingly intricate series of steps.
Unlike Hubble, we are not orbiting the Earth. We're going straight out 1 million miles where no man has gone before. So servicing is not an option for us. All the release mechanisms have to work. If they don't deploy, we've had a bad day.
We allow the telescope to cool down and the instruments to cool down, and then we start focusing them. That takes altogether 6 months to get all of that set up. And then we're pretty ready to say, let's try some science projects. Webb telescope has 4 instruments altogether. One is a near-infrared camera. It's the most sensitive of the instruments. Number 2 is a near-infrared spectrograph. That one spreads out the light of the stars or galaxies into the spectrum. A special invention that we made for that one was the micro-shutter array, where you measure 100 separate galaxies at once. The third instrument is the mid-infrared instrument, or MIRI. That's a special one because it picks up wavelengths where the molecular emissions are the strongest for the coldest objects out there. We'll be able to look way back to where we think the first objects may have been formed in time. The fourth instrument is the slitless spectrograph. It is used for extremely high angular resolution images that might have planets in them.
On average, every star in the galaxy has at least one planet. So when you look up at the sky, the pinpoints of light you see are planetary systems, not just stars.
We are super excited about the launch of the James Webb Space Telescope because it's going to bring us new data about planet atmospheres, and my mom and I are going to be working together on sort of disentangling that data. My mom is discovering new planets, and I take those planets and I try and understand what their atmospheres are like.
Most planets that have been discovered were noted because we observed something about the star that indicated the presence of a planet in orbit around it. You're measuring the brightness of a star, waiting for the momentary dimming of light that happens if a planet in its orbit around the star happens to pass directly between the star and the telescope. we discover evidence of a planet buried in data. And that can feel like an abstraction. We have to pause and remember that these places really exist. Someplace there's a lava ocean rising and falling with the tide. Someplace there's an eastern horizon where 2 stars are rising, not 1.
We've only really been able to scratch the surface in terms of what we know about those planets. But now with the James Webb Space Telescope, we'll be able to dig deeper and understand more about what their atmospheres are like. By looking at the atmosphere itself, you can actually get an idea of what the climate is like, and you get an idea of what the full chemical makeup of the planet is. We want to study those atmospheres because we think that there could be potential signs of life encoded in those atmospheres. Here on Earth, we have a very specific chemical makeup in our atmosphere that allows life to flourish. Geology produces methane, but life produces methane in 100 times higher quantities. And so if we can look at this delicate balance between CO2 and methane on other planets, that could give us some indication of life. One of the most exciting planets that JWST is going to look at is the TRAPPIST-1 system. This is a star that's just about the size of Jupiter, so it's very small, and it has 7 Earth-sized planets orbiting around this star. 3 of those planets could be potentially habitable. Looking at those planet atmospheres is going to be like this perfect laboratory of science where we can sample the atmospheres of 7 different planets.
Potentially habitable Earth-sized planets are relatively common. We expect there to be maybe 12 billion such worlds in our galaxy alone. Earth didn't make its appearance until billions of years after the Milky Way formed, but there are planets that formed in those very earliest moments of the Milky Way. And imagine how life could evolve on a planet given 10, 12 billions of years of evolution.
Webb, because it's so powerful, you can't predict what it's going to see.
We have lots of reasons to be skeptical of our understanding of the very early universe. We have a pretty good story called the Standard Model of the Universe, which is cosmic dark matter, cosmic dark energy, ordinary matter, and gravity pulling things together after the Big Bang. But people don't have any explanation for where did the dark matter or the dark energy come from, and we don't know that that's the only kind of stuff out there. So I think we could get a big surprise way out there in the early universe.
I'm hoping, in my heart, that James Webb finds a whole new field to investigate. Even though I'm 62 years old, maybe I can go back to grad school, get my PhD on something in a brand new field that was started by James Webb.
Every time astronomers build a powerful new tool, we discover something new. Nature has more imagination than we humans have.
What makes us human is to be curious and to push boundaries and explore and increase our understanding of the universe. JWST is the next piece of that puzzle.
We are learning about our galaxy at a very rapid pace. We've gone in just a couple decades from finding the very first planet orbiting another star to having a comprehensive, specific plan for identifying living worlds. I really hope that Webb helps me to understand what fraction of the planets orbiting in the Goldilocks zone are true Earth analogs. I feel confident that my grandchildren will be able to look up in the sky and point to a star and say, there's life. I think that's going to be a moment more profound than our Copernican moment that took Earth out of the center of the universe. It's going to put an end to cosmic loneliness. It's going to fundamentally change what we see when we look up in the night sky.